going to be a straightforward single reagent. Okay? Minimally, what you should be doing when you look for these things is say what things changed. So what changed? When you look at C, pi bond and bromine and our oxygen. So we're doing an addition reaction. So minimally what we would expect to see for reagents, and I'm going to do it above and below the arrow just because I need space. Minimally we need to see something along those lines. We need the bromine, we need the OCH3, and we got to do something with the alkene. Okay? At that point you would hope one multiple choice answer gives you that. If not, now we got to look a little bit closer. Okay? In the process of looking a little bit closer, we need to evaluate what the reactivity is of each of these. When our alkenes react, what do? Every single time. It's the pi bonds, and in particular, what about the pi bonds? They have electrons. They are an electron donor, which means our alkene is going to be negatively charged. There is no choice. We're looking at that as our negative. Bromine and OCH3. Both negative. Anybody have a problem with that? We need a positive for this to be able to react. So that means one of these reagents is going to have to get changed such that it can become positive. Oxygen being the most electronegative element on the planet, or not on the planet, sorry, that was a bit excessive. Second most electronegative element on our periodic table is not going to really be able to be bound to anything to make it positive. Okay? On one side of it, it's bound to a carbon. It's going to be taking electrons from that carbon already. Okay? So the oxygen is going to have to stay negative. Our alkene was given to us, so we can't change that because we were given that. That's what we're starting with. So it has to react as a negative. That leaves only one option left. That bromine must be positively charged. For it to become positively charged, it needs to be attached to something that can take the electrons away from it. Attach it to another bromine. Okay? And what we now have is Br2 reacting in the presence of that OCH3 minus. This general reaction does not require a strong nucleophile, so we won't end up adding it as OCH3 minus. We'll add it as methanol with the hydrogen attached. Okay? Look for the pieces that need to make it into the structure and then start to evaluate where you can source these. Okay? A common reagent that floated out there for that bromine, I almost guaranteed you'd see this as an answer, would be HBr and RHOCH3. Okay? That won't work because the bromine is negative, the oxygen is negative. This is why we went through that initial assessment of what typical charges would we see on each of these pieces. For this reaction to work, one of those needs to be positive. The oxygen can't do it. The carbon can't do it. That means the bromine has to be positive. HBr does not work as a reagent because HBr generates a negative bromine, not a positive one. Okay? Makes sense? I'll accept that as a sort of yes. Okay, what happens in M? What changed? Hydrogen and bromine, and we lost the alkene, so we're doing an addition reaction. Minimally, we would need hydrogen and a bromine. Is HBr the correct answer?
It's part of it.
It's part of it. Is it going to give you the correct answer?
No.
Why not?
Because it won't become a radical.
We have to realize how this reaction works. The alkene acts as a negative, picks up the positive hydrogen first, okay, and the hydrogen would go where?
At the least substituted.
The least substituted, which would give us as a product shown in red. So we've got the right pieces, but we need something to cause this to do the opposite of what it would typically do. What's going to cause things to do the opposite of what they typically do? Radicals. How can we force the radical? Light and heat are a typical signifier, except that only works if we have a non-polar bond with very electronegative elements. We're looking at carbon-carbon. That's non-polar, but that's not an easy bond to bust. HBr, that is extremely polar, not going to break homolytically with light. So what we need to add is some kind of radical initiator. Heard a couple good options. The ROOR would be what you would need. So your official answer needs to be with the HBr and the ROOR, okay, our radical initiator. That's going to get us the proper arrangement of those species. Okay? So just identifying what changed doesn't guarantee you the answer. You're also going to have to realize how those reagents work. So take a guess, draw out the reaction. Make sure that the reaction that you're suggesting leads to the product that's actually presented. Q, what makes Q kind of obnoxious? No rearrangement. This doesn't happen super often in the ACS test. I did go through and check this. This question actually tests on two things. Do you understand reactions and nomenclature? Okay. I think it only pops up 2 or 3 times at most on the ACS test where they're asking you a question about a reaction where you need to know nomenclature as well. Okay. In most circumstances, if they want to ask you about nomenclature, they ask you about nomenclature. If they're going to ask about a reaction, they'll ask just about the reaction. You don't need to know both. It does pop up, so you need to be aware of it. So the very first thing we should go through and do to solve this problem, draw out the structure. 1, 2, 3, 4, 5, 6. We're starting with 1 bromohexane, and we're ending with 2, 3, 4, 5, 6. Kind of out of space. Sorry, I'm going to have to put it over here. 2 hexanol. All right, this is one that we will talk about at the end because alcohol nomenclature can pop up. We won't look at its reactivity too much, but you can see its naming show up. Alcohols are our highest priority group as far as we're concerned this semester, which means they will end with their little nomenclature stint. How do we know it's an alcohol? It's the OL at the end of that name. OL signifies your alcohol. How do we know it's all single bonds? It says an all. How many carbons are in our structure? 6 because hex. Where's the alcohol located? At position 2. Okay. So it's breaking each of those names down into those structures. So looking at this result, what has to happen? Bromine has to leave, and I would need to put on an alcohol. So we could push conditions where we just add an alcohol. Add the OH. Okay. What would that OH need to come in as? Negative. Well, we'll talk about this. More than likely, our oxygen is going to be negative. Very rarely can we get a positive oxygen. Okay. It would come in, do a backside attack, and kick out that bromine. So what alcohol would we have? 1 hexanol. Not our answer. So at some point, we do need to address that OH, but we can't address it right away. We have to somehow shift reactivity from our 1 position to our 2 position, because that's where the OH attaches. We'll do an elimination reaction. The elimination will get 2 carbons that are now potentially reactive. How can we facilitate an elimination reaction? We want to use a sterically hindered base so that it acts less like a nucleophile. So that negative OH, or that negative oxygen, wasn't a bad idea, it just wasn't sterically hindered enough. We could add something like T-butoxide. The result of that first step, I'll show in purple, we'll end up with our hex structure, 1, 2, 3, 4, 5, 6 carbons with our hex, and we now have our alkene. Now that 2 position has some reactivity associated with it. What should we react it with? Minimally, what do we need? You need the OH. OH doesn't react very well as a negative. We need to make sure our carbon somehow becomes positive. To do that, we need to react our alkene with something else first. One option could be H+. If we react the alkene with H+ first, where's that hydrogen going to go? It'll go to our least substituted position, putting the hydrogen here. What would be left on our position 2?
Carbocation.
A carbocation, which could then react with our water. So we could do H+ and H2O, and we now have our final product.
Is it not possible to do a substitution where a reaction or where a rearrangement takes place?
On this one, not cleanly.
Oh, okay.
Yeah. There's nothing to force that rearrangement in this at all. The bromine would have to leave to get you something unstable to allow for the rearrangement, but the bromine's not going to leave because it leaves a primary carbocation.
Gotcha.
Okay. What other reagent would work for this? Or what's the issue with our H+ and H2O? Maybe you guys remember that one. Form a carbocation. It can rearrange. So we could actually push 3-hexanol because that carbocation could shift further into the structure. It's not going to be very likely because it's not becoming that much more stable. But if we want to guarantee that we only get the 2-hexanol, we need to go through and use a reagent that will put that alcohol at that position but not give us a carbocation. What reagent does that? That's our mercury one. So it would be mercury OAC 2 in the presence of water, which puts on our OH at our 2 position, but then it also leaves us with a mercury at our 1. How do we get rid of the mercury? Good start. Sodium. What needs to go on that position? We need a hydrogen. Mercury is positive, so we need a negative hydrogen. Where do we get negative hydrogens for? Also known as negative hydrogens? Hydride. What reagent do we know of? There's only one so far that mentioned it. Sodium borohydride. Okay. So these types of questions you will absolutely see on the ACS test, being able to predict what pieces can shuttle in and out. Okay? I doubt with this last one you would be given both H+ and water and the mercury reagent, because both of them would technically work in this circumstance. The mercury would work better. Okay? Everybody's favorite kind of test. Which of these is the best answer? Tend to not get those on the ACS test. You get more kind of straightforward. Okay, so I don't expect to see that balance between those. Right. Worst case, you do see it. You're at a 50-50 choice. That's not bad. That's passing the test. So be happy with getting it down to a 50-50 choice. Okay. B would be the last one. B's tricky. What's the net result in this? We're making an alkane, which means we're pretty much substituting a hydrogen for the OH. Don't really know how to do that. Okay? There's a couple methods that we could go through. The method that we'll talk about today would be to take this down in an elimination reaction. So add concentrated H2SO4, just like we did in lab, which will give us an alkene. So this is the result of step 1. Once we have the alkene, we can react that in a situation where we need to get to our final product, which is where we've gotten rid of the alkene by doing what?
H2.
Adding 2 hydrogens, also known as H2. What we'll see is that molecule is so small and so reactive that we need a catalyst to initiate that. You'll see it typically with H2 and palladium, or platinum, or even nickel. pop up in there. All right? So identify what needs to change. Find a reagent that matches that as close as you can. All right? Is this a lot to process? Absolutely. All right? But that's part of what organic chemistry is. Looking at those pieces, identifying what changed, and starting to put in whatever you know. If you don't know it, it's multiple choice. Yes. Okay? Questions with any of those? Okay. Alkynes are effectively alkenes. All right, we've already addressed one of those big differences, and that's that our hybridization changes. Yes, you'll see questions on hybridization. We're looking at a carbon in the alkene that is what hybridization? sp2. And our carbon, or our alkyne, our carbon is sp. The less hybridized, the more electronegative it becomes, because we're looking at more S character, which is held closer to the nucleus. That increased electronegativity of that carbon causes that hydrogen to become Bronsted-Lowry acidic. Okay? Which means, given the proper circumstances, we can have the carbon take the electron density away from the hydrogen, and what we end up with would be this structure, known as the acetylide ion. Why is that species pretty cool? Relatively. It's a nucleophile. How often do we have carbon nucleophiles? Fairly rare. Okay, why? Carbon is small and not very electronegative. Okay? So if we put in the proper, or put our acetylene in the proper circumstances, we can generate the acetylide ion, and it can now react as a nucleophile in any circumstance that requires a nucleophile. Okay? And in particular, what type of nucleophile? Strong nucleophile. Okay, why is it strong? Negatively charged. Okay? To get this to work, we do need to add a base to our alkyne. Okay, so what base do we know of? OH minus, good reasonable base to use. That's what we've defined as a strong base. It turns out OH minus is not strong enough. Okay? We have to use an even stronger base. That stronger base is going to be, is Br minus a strong base. That's actually an extremely weak conjugate base because that makes strong acid. You got the right idea. You're shifting on your periodic table. You just shifted the wrong way. Go the other direction of oxygen. Instead of going to the halogens, go to nitrogen. Why would nitrogen be more basic than oxygen?
Less electronegative.
It's less electronegative, which means it's more willing to share its electrons with that hydrogen, and it facilitates that deprotonation. The base that we would end up using, whoops, that's an eraser. Pretty much the exact same thing as sodium hydroxide, except we now swap in a nitrogen instead of the oxygen. But we have to account for nitrogen's exceeded octet, not exceeded octet, but it's larger octet, and we have to account for 2 more hydrogens. That becomes a negative charge. That can then attack the hydrogen. Hydrogen has too many bonds, shuttles the electrons over to our carbon. We now have the acetylide ion.
Are there other bases that we could use for this?
Yes, this one happens to be the one that's shown pretty much exclusively everywhere.
Gotcha.
Okay. But yes, there are other strong bases. For instance, if we take one more step to the left, we can get a negative carbon. Okay? Negative carbons are really strong bases. They could also act in this. The issue is that's what we end up with in the end of it, but we can tweak the electronegativity around to make it a stronger base. Okay? This reaction still isn't a perfect shift. We are in an equilibrium situation, but we do tend to favor the acetylide in this case ever so slightly, and that's because of the stability of the ammonia. Okay? How can we hide that negative charge? Make it look like, oh my gosh, it's an entirely new reagent? Just put a metal next to it. Okay, we now have a metal-non-metal bond, which is ionic. That dissociates, and we have sodium plus and our NH2 minus. Okay? So the typical reagent for your acid base with your alkynes is sodium amide. Okay? Amide, just like hydroxide, we're turning that ending into an IDE. Okay? So there's our reagent, sodium amide, to get that acid-base conversion. Okay? Before I do that, what happens if I react the alkynes, say, with bromine? What would I expect? What does Br2 do? What? We do see a change in color if we're going to use it as an unsaturation test. But what's happening to cause that change in color? What happens to the bromine?
It's not Br2 anymore.
It adds across the double bond. So when we added Br2 to an alkene, we ended up with our carbons with bromines attached. And then whatever else was out there. I don't feel like drawing all the R's and H's. Okay. What's going to happen with the alkyne?
Same thing.
The exact same thing. So we'll get rid of one of those pi bonds, put on our R group, and put on a bromine across both sides. But now what functional group do we have?
Alkene.
An alkene. What do alkenes do in the presence of bromine?
Same thing.
Same thing. React with another bromine, and we end up with an alkane with 4 bromines around it, in our R group and our H group. I know that looks sloppy, but hopefully you get the idea. What if we... It is a bromination reaction because we're adding strictly bromine. What if we added HBr? What does HBr do to a double bond?
The Br
Adds bromine and
adds hydrogen.
adds hydrogen. What's going to happen with a triple bond? It's going to add 2 bromines and 2 hydrogens because there's 2 pi bonds. Okay? So your alkynes react very, very similarly to the alkenes. We ultimately get kind of the same reaction all the way through. There is some exception to that. Okay? That exception is what's listed on your slides. Reagents that turn an alkene into an alcohol with our OL, okay, will turn an alkyne into a carbonyl, either a ketone or an aldehyde. Interesting. Why do we end up with that different functional group? Okay, well, it's going to come back to what's happening within each of those reactions. So let's pick a reagent that turns an alkene into an alcohol. So here's your pop quiz again, just like we just did. I want the reagent that's going to give me this as an answer. T-butoxide would do an elimination reaction. We need to do an addition reaction. What are we adding across the double bond? We're adding the hydrogen and the OH. So if we just guessed and said let's put in H plus and our OH, where would the H plus go?
To the least substituted.
To the least substituted. Is that what our answer shows?
No.
No. So we need something to put the O, or have our hydrogen go to the most substituted, or our OH go to the least substituted. What reagent gives us the opposite result? It's a big hint. It's 2 steps. Radical is not a bad idea. Unfortunately, it's not radical. Someone's really been studying. BH3 and THF. That will add hydrogen, okay, as a hydride going in as a negative charge, so it's going to go to our most substituted position, and our boron will go into our least substituted position. as our positive. We can then cleave off the boron by adding peroxide and hydroxide. I know, I'm pretty sure when I showed it the last time I did hydroxide first. But we have to add that peroxide and hydroxide to cleave that off. Those two will almost always be paired with each other because we don't want to end at the boron structure, we want to end with our alcohol. So if we use that sequence of reagents, we put our alcohol on the least substituted position for our alkene. Okay? So let's pretend we didn't actually show out this reagents thing for a moment. Let's go through and say we're going to use the same reagents with the alkyne. What would you predict the result to be? Okay, at least as a first stopping point. Any ideas? Should it do anything to the R? When we use that reagent, what does it react with? Reacts with the pi bond. So let's get rid of one of those pi bonds, which means we still have two, or one pi bond left and one sigma bond. Then we'll have our carbon, we'll have the other hydrogen. And our boron reagent adds hydrogen and OH to that pi bond. Where should the OH go? Our least substituted position, and our hydrogen should go to the most substituted. Okay. I always find this reaction kind of mind-boggling and different, mainly because we've generated a new functional group here. Okay. We have an alcohol right next to an alkene. Because those two functional groups are close to each other, it actually changes the overall chemistry of both functional groups. And it changes the properties of it. What ends up happening is the functional group that we now have has both an alkene. How do we refer to our alkenes? We name them based on calling them enes. And we have an alcohol. How do we name our alcohols? What functional group do we have? An enol. We have an enol. What does that enol do? We're going to do this as a very abbreviated mechanism. The oxygen, being more electronegative than that hydrogen, will take the electrons away and push towards the carbon. Now that carbon has too many bonds, so what happens to it? We're going to have to break a weak bond. We're going to break the pi bond. That pi bond is going to go out and pick up an H+ from solution. The result, it's officially a couple-step mechanism, gives us this. What functional group is that? It is a carbonyl. Take it a step further. It's an aldehyde. Okay. The carbonyl is just that stretch right there. As soon as we put a hydrogen next to it, it becomes an aldehyde. So that in orange is our carbonyl. Our aldehyde is officially going all the way out there. Okay. Which functional group have you heard of before, aldehydes or enols? Which one do you think is more stable? What's the product of this reaction? The aldehyde. Right? Without the alkene anymore, can we do the addition? Nope. No alkene, no more addition, our reaction stalls right here. So when we react our alkyne with our boron reagent, we end up with the aldehyde. We're still adding hydrogen, we're still adding OH. The process or the issue with that is we end up with this crazy intermediate that goes through its special, it's known as a tautomerization, to make the more stable carbonyl structure. Okay, can I erase that? Or are we still writing? Okay, I'll slowly erase. Instead of BH3, I now want to add my mercury acetate in the presence of water. And I'll follow that up with sodium borohydride. What would that do to my alkene? Hydrogen's least substituted. Alcohol's most substituted. All right? Seen that one before. Let's move to the alkyne. We're going to use those exact same reagents. What happens with our alkyne? Oh, I hope you're done with that last part now. We're going to end up with the exact same result. We'll put our hydrogen at our least substituted position and our alcohol at the most substituted. What functional group is right here in orange? Enene. What functional group is now in green? I know, the horrible color. Enol. What functional group do we now have? Enol. Are enols stable? Nope. What ends up happening? Our oxygen takes the electrons away from our hydrogen. Our pi bond comes out, picks up an H+. In a sequence similar to that, what we end up with that functional group known as, it's not an aldehyde anymore because we don't have a hydrogen attached to the carbon. We have a ketone. Remember way back at the beginning of the semester I said you needed to memorize all your functional groups? You should probably go back and do that. There are definitely a few questions that go or ask about functional groups. All right, so in orange we've got the carbonyl. If our carbonyl has carbons on either side of it, we've got our ketone. All right. What happens if instead of adding the mercury, we just added H+ and H2O? Hydrogen goes to the least substituted, OH goes to the most substituted, which is then going to form the exact same thing as our mercury, our enol, which then goes to the ketone. So any reagent that adds water across a double bond, right, when reacted with an alkyne, is going to turn into the corresponding carbonyl-containing compound, either the ketone or the aldehyde, depending on the reagent, okay, because it's going to depend where it's putting those atoms. Okay? The part of this that I think is kind of a bit sketchy to throw in at you guys now, but this is the way it works. The enol, really, really famous compound. Pretty much all reactions within the Krebs cycle revolve around enol chemistry. Okay? So it is massively biologically important. Okay? We'll devote an entire chapter, maybe even 2 chapters in second semester to enol chemistry, because it does all sorts of fun, crazy things. Lucky you. Okay? But this is where it first pops up. Like I said, we'll talk about it in a lot more detail in second semester. So, let's do D and attempt E. E is, again, one of those kind of tricky ones. What reagents would you use for D? I'll give you a minute. Look at it very carefully. So, why can we not attempt this one as easily?
Not only is the oxygen getting added, there's more carbon.
Actually, I lied. No, I double lied. You should be able to do this one. I triple lied. Because it's a more difficult one, let's actually kind of step through and look at what things changed. So what do you guys notice?
Turns into a ketone.
So we've got a ketone. How do we make the ketone?
Mercury. All right.
Okay, our ketone came from an alkyne and our mercury reagent. Okay. But is that all that happened? Isaac, what else did you see? There are 2 more carbons. Where are those 2 more carbons? So this is another fun part. Okay, we've increased the number of carbons. If we're going to try and figure out what reagents we used, we had better identify what carbons actually were added to the structure. Because if we don't know where they came from, okay, or where they ended up, we can't do anything to be able to predict where they came from. All right? How many carbons in your starting material? 4. Where's the reactivity in that starting material?
Between 1 and 2.
Okay. Our triple bond looking at carbon 1 or 2. Okay. I'd focus on carbon number 1. Where is carbon, or where's the chemistry in our product?
At carbon 3.
Okay. Right at that carbon. Our most reactive carbon is likely going to be the most reactive carbon in both the starting material and the product. What does that mean? The carbon that we circled is our most reactive in our product, and the carbon that we are now circling as our most reactive carbon in our starting material are likely one and the same.
So we're adding the carbons to that carbon there.
So we are adding the carbons to that carbon, which means if we look at our product, where are our new carbons?
At the end of carbon 1.
All to the right. It's those 2 carbons. All right? So somehow or another, I have to link carbons with each other. Not easy. Why? Because carbons aren't good at becoming nucleophiles. So let's look at our reagents. Can we make our carbons a nucleophile? So we're going to have 2 carbons here. One's a CH3, one's a CH2. Can I make the CH2 a negative, or can I make my blue carbon a negative?
The blue one can be negative.
How can I make the blue one a negative?
Electrons from the carbons.
No. Take the hydrogen off. Remember, we're looking at the hybridization. That carbon is now sp hybridized. It is more electronegative. I can react that species with sodium amide. That's then going to give me my CH... Oh, man, all these stupid carbons. Triple bond, carbon, negative carbon, which means what does my purple CH2 need to be charged? How can I get that carbon to be positively charged? Is carbon going to take electrons from hydrogen? No, that's not going to... Or even the other way around. Is hydrogen going to take electrons from carbon? No, that's even worse. Oxygen's a possibility, except if we throw in oxygen, we're also bringing in a hydrogen. What charge does that hydrogen carry? It would carry a positive charge. Our negative is going to react with the most positive. The most positive will be hydrogen. We go backwards. So oxygen's not a good option to attack to our carbon. We need a good leaving group like a bromine or something. Awesome choice of words. One, and I actually meant that as a good thing. It didn't come out that way.
Okay. Okay.
We need to generate our carbon as a positive so we can attach a halogen to it. Good leaving group makes that carbon positive. The result of that reaction, so if we look at each of our results, man, I'm going to start drawing out all these stupid carbons again. The result of each of these steps is that we end up, first off, making our carbon more reactive, but then we also extend the carbon chain. How many carbons do we now have in our structure? How many carbons do we need in our structure? We've got our carbon chain. Can we convert that triple bond now into a carbonyl? We can go through and do another step here to go ahead and put on our carbonyl. We can go through and use either the mercury reagent our H2O followed by a sodium borohydride, or for that matter we could use the boron reagent, or we could even use our H plus and H2O. So the end result, to go through and do that one problem, we had 3 steps. What happened in step 1? What is that chemistry? Acid-base chemistry. What happened in step 2? Substitution. Just to be obnoxious, which mechanism? SN2, strong nucleophile with our acetylide and a primary substrate.
Didn't they have to form that carbocation to even react up?
Carbocations is SN1. That's why it has to be SN2. So no carbocations.
What's
We don't.
so that thing that you drew above there, that carbocation above there, is fine?
So that carbocation is there to identify what that charge needs to be. That charge needs to be positive.
Gotcha.
Okay. How do we make it positive is the next issue. What mechanism would we run by? We'd start to refine where that came from. It's not an official structure, no.
Gotcha.
Okay, good question in that respect. Last one. I guess that last one's a little bit, oh no, that one should be straightforward. It's an addition reaction. You've strung together 3 different types of reactions to generate one new product. This is where we're going with organic chemistry. How do we build these larger structures based on the pieces that we know we have, and how can we force them to occur in the way we want them to? Okay. This is why it's fun, because it's not reading a book and saying, tell me the answer, okay, like biology. It's looking at a product that biology made. It's not just you guys, there's lots of biologists in this class. It's looking at a product that perhaps was made in biology and designing a way to make that on our own. Okay? Really, really important for drug synthesis. Beyond that, I think it's just cool. Okay? You can disagree with me, that's fine. Okay? But that's where we're trying to get with organic chemistry. Being able to look at where we see chemistry occurring, how does that structure change, what reagents can we use to slide these pieces in and around to be able to build these overall larger structures. Okay? Kind of fascinating stuff. Stuff of legends. Why not? Okay. Part E is difficult? Nope. What's going to happen with E?
Doesn't have to go all the way.
That one you're actually running into an issue as well. We're going to run through and do our mercury with that. Okay, I'm just going to abbreviate as our mercury, followed by step 2, our sodium borohydride, which will get us to the ketone, but we don't want a ketone, we want an alcohol. H plus will put a hydrogen on our oxygen, but then what charge does our carbon become? It would become positively charged. So what we want to add across this structure is not just H plus, but H minus. We can do that by adding H2 with our palladium or platinum. Okay? Which works out nicely for our next step, looking at redox reactions, which I'm going to cover in the next 30 minutes, the next 14 slides. I will definitely gonna do a recording on some of this and get this posted because we need to get this material covered, and I want to kind of leave next week a little bit more open. Okay, so you will see a recorded lecture on your redox on what we don't get covered here. When it comes to Gen Chem, hopefully you guys remember, reduction is gain of electron, oxidation is loss of electrons. However you want to remember that. I personally remembered the Leo says Gur, other people did oil rig, all that fun stuff. That is great for general chemistry. Here's a new reaction. What species would oxidize? What species was reduced? Not quite as easy to pick up. We could officially go through and determine the oxidation states to figure everything out. It's going to be a lot more work than it is necessary. So what we'll switch to is a slight tweak to our rules. Our reduction is an increase in the number of hydrogen bonds. Not the force, but actual bonds. Or a decrease in the oxygen bonds. Oxidation is an increase in oxygen bonds or a decrease in hydrogen bonds. Okay? So we got two ways to look at each of those reactions. So let's take a look at our reaction again. Okay? That whole reduced versus oxidized, we can switch a little bit because in organic chemistry, what are we concerned about? Only the organic compound. So I'm going to take a look at my reactant, that cyclopentadiene. What happened to it to go from there to our product? We had to increase the number of hydrogen bonds, which means that species was reduced. We would classify that reaction as a reduction reaction. Bit odd. Okay, why is that a bit odd? Come on, Gen Chem. If you have reduction, what else is present? Oxidation. If you have a reduction reaction, there's also an oxidation. So typically when we look at these kinds of reactions in Gen Chem, we refer to them as redox reactions because both are happening simultaneously. Are both happening simultaneously in this reaction? It has to be.
The H's are decreasing H bonds.
The hydrogens, or that H2 molecule in the middle, changed its oxidation state. So if our carbon structure was reduced, what happened to our hydrogens? They were oxidized. And as Jerry was pointing out, I didn't even realize this, but it works, we actually decreased the number of hydrogen bonds. We started with a hydrogen bond between each of those hydrogens, and what did we turn them into? Carbons. Okay, so H2 was actually oxidized. Okay, so it does actually match with those definitions. Hallelujah. Okay. Why do we use hydrogen and oxygen typically when looking at these things? Why is it easier?
Hydrogen is always being added to the outside, so it's easier to put the outside versus.
What's the availability of each of these reagents? Really, really good. Okay. Typically these reactions were coming from the definition of oxidation, which was the increasing of the oxygen molecules or the consumption of oxygen molecules by a particular species. Say iron to make rust. We increase the oxygen presence, so it's oxidation. What happens if we decrease the oxygen presence? Well, we've reduced. Okay? So it all kind of centered around oxygen to begin with. When we shifted to organic chemistry, we could also see the hydrogens jumping into this as well. When you go through and evaluate your reactions, oxygen isn't always present in a reaction, like we very clearly see with that top example. Okay? So what we could look at is use our hydrogens. But what if we don't see hydrogens or oxygens? Then it becomes a little bit more difficult. It doesn't have to be oxygen. What we're looking at is an increase in more electronegative bonds. Okay, so anything more electronegative, if we increase that type of bond, while at the same time not doing the other thing, okay, then we're okay. Then we're looking at a reduction. Okay. Could we apply that definition back to our reaction up here? Did we decrease more electronegative bonds? Hybridization of our carbons, or most of the carbons in our starting material. sp2 in our product.
sp3.
What changes as we change our hybridization? Electronegativity. We went from sp2 to sp3. We became less electronegative. Did we decrease the number of electronegative bonds? Absolutely. Okay. It does still match. It does still fit. Okay. So what you're going to be responsible for is looking at a reaction and deciding is it a reduction reaction or oxidation on top of all the other ones. So we'll run into some new reagents with that as well. Real briefly, if you do want to come up with oxidation states, I'm horrible at figuring these out. The first time I attempted to explain this theory, I got it wrong, okay? Because the other definitions work a lot better, okay? So if you're forced to determine the oxidation state for, say, carbon in methane, what we can go through and do is cleave all of the bonds homolytically. How many electrons would be around the carbon? 4. Homolytic cleavage. Minus the heterolytic cleavage. Which is more electronegative, carbon or hydrogen? Carbon, which means the electrons in each of those bonds should go where? Carbon. How many electrons would be around the carbon in methane? All right, let me write it out again. If we do the homolytic cleavage, this abbreviation is going to be bad, but whatever. In our homolytic cleavage, we break each of those bonds. They go back to their parent atoms. How many electrons are around the carbon? 4. Minus the heterolytic. Right? So in a heterolytic situation, what we're going to do is push the electrons to the more electronegative atom. Which is more electronegative, carbon or hydrogen? Carbon. So let's take both electrons in each of those bonds and put them onto the carbon. How many electrons are in a bond? How many bonds are there? 2 times 4. Oxidation state of the carbon. -4. It is fully reduced. We're looking at the smallest oxidation state possible. Let's go ahead and look at the fully oxidized state, the extreme spectrum of this. Homolytic cleavage. How many electrons does our carbon have? Heterolytic cleavage. How many electrons does our oxygen have? Sorry, carbon. In a heterolytic cleavage, we're going to take each of those bonds and move the electrons towards the more electronegative atom. Which is more electronegative, carbon or oxygen?
Oxygen.
How many electrons are around the carbon now? 0. What's the oxidation state?
4.
+4. Fully oxidized. Okay. The bigger the number, the more oxidized your molecule. The smaller the number, or the more reduced the number, the more reduced the structure. Okay? So we could go through and label reactions as reduction, oxidation, or neither, depending on your preference. Because of time. Right side of the class, do the right side of the problems. Left side of the class, do the left side of the problems.
You're right.
Doesn't matter. It really doesn't. Because I'm only going to give you a minute anyway.
Those rules are centered at carbon.
They're all centered around carbon. Why would we center on carbon? It's organic chemistry. Okay? So being able to identify these, you'll see a bunch of these pop up in the sapling homework. You might see 1 or 2 of this kind of difficulty, saying whether it was reduced or oxidized on the ACS exam, but you won't see a whole lot. They'll be more concerned about the reagents that cause these types of conversions. Okay? As far as those reagents go, we're only going to be concerned about reagents that react with our alkenes or our alkynes, which means the really easy ones with oxygen increasing or decreasing, we won't worry about those reagents. We'll see those next semester. Okay? Our reduction reagents, I've listed 4, though really we've got 3. The only reason I split up those first 2 was just because you might see the term rainy show up in there. I think your textbook actually lists palladium, platinum, and nickel, all as kind of one possible option. Those are ores for each of these. So if we add hydrogen, gas, H2, and palladium, it does a reduction. We add H2 gas and platinum, does a reduction. H2 gas and rainy nickel,
Reduction.
still a reduction. Okay? Nothing's going to particularly change. All 3 or both of those reagents / different catalysts will all completely reduce. So that means that they will take out any double bond and completely turn it down, or completely reduce it, get rid of it, and saturate it with hydrogens. Okay? How does it end up working? Okay? Kind of similar to the idea with our bromine. Okay, when we did our bromination reactions. Bromine added bromines across the double bond. We're doing the same thing with hydrogen. The issue with hydrogen, it is much, much smaller. So I can't polarize that bond as easily, which means I don't have a positive and I don't have a negative. So to get it to react with the alkene on its own, it just doesn't happen. Okay, so that's what the catalyst is there for. That metal catalyst will allow for the passage of electron density from the hydrogens and from the alkene to properly get the bond arrangement to occur. Because it happens on the surface of the catalyst, that is going to force very particular chemistry. Okay, when we looked at the bromination reaction, our bromide could come in from the backside because it could freely move. It wasn't attached to anything. If I attach both the hydrogen molecule and the alkene, the hydrogen can't jump over to the backside. It has to come in from the same side of the double bond. Okay? What does that mean as far as the addition reaction? We get a syn addition. Okay? So if you have a cis or trans double bond, the arrangement of the rest of those alkyl groups on the double bond are going to be forced into that stereochemistry because of how the hydrogens add to that double bond. How is that going to become increasingly confusing? I know it's really small, but let's take a look at that very end structure with that alkane. What kind of bond is between the two carbons? What can sigma bonds do?
Rotate.
They can freely rotate. More often than not, you'll go through an addition reaction with hydrogen, and instead of them keeping it in the nice orientation where you can see that the hydrogens were added on the same side, they'll rotate one of those atoms that now makes it look like the hydrogens were added on opposite sides. Okay? So it becomes a lot more difficult to interpret. Rotate it back to the proper alignment to ensure that your hydrogens are added syn across the double bond. They're added to the same side of the double bond. And that's all because of this metal catalyst forcing that alignment. Okay? Without the catalyst, hydrogen isn't polarizable enough, can't react with the alkene, so we end up adding the hydrogens to the same side. Okay? It's really only going to be super important for our alkenes because we have that cis-trans issue. With our alkynes, will it become as important? There's no cis-trans, which means if we add all the hydrogens onto it, there's nothing to change. There is no stereocenter. With the cis-trans, we will end up with a stereocenter. All right, so you got to watch out for that with your alkenes. A little bit nice with the alkynes. Move. There we go. What happens with our alkynes? So this is going to require drawing it out real quickly. If I add hydrogen and platinum, all right, let's just say I add one equivalent. All right, so the equivalent just means that the mole ratio between the alkyne and that hydrogen are exactly the same. So I can only add one molecule of H2 to the double bond. What's the result? I'm going to have a double bond. And I'll have an R prime, and I'll have an R, and I'll have my two hydrogens attached to it. Is that the only possible product?
Could be the opposite.
We run into an issue because what happens if we change the reaction around? We could end up with the trans alkene. In the case of the H2, palladium, platinum, and nickel, okay, for all three of those, the catalyst is so reactive that what ends up happening?
Both the pi bonds?
Both pi bonds react. Does it matter now whether it was cis or trans? No, because when we look at our product, no stereocenter. We've added two hydrogens to both those carbons. Okay? The special part, Lindlar's catalyst and the sodium metal in the presence of ammonia will actually not react with alkenes, which means if I switch to those reagents, I will stop at the alkene. Which of those two products you think is going to be favored if we use Lindlar's catalyst? Lindlar's catalyst is poisoned platinum. Okay? So it does the exact same thing as platinum. Which of those two products would we expect Lindlar's catalyst to have generated?
Cis, because they have to have the same side.
Cis, because the hydrogen gets added on the same side. That's what our platinum catalyst does. So what we're looking at with our Lindlar's, we get our hydrogens added syn across our triple bond, and we end up with a cis product.
Why doesn't it react with or do they just doesn't matter?
That's what the poison does, is it prevents the alkene from attaching nicely. And as Janine was suggesting, trans is more stable. Okay? So if we have an intermediate that allows for free rotation, then yes, we would expect the trans. Which reagent allows for that? The sodium metal in the presence of ammonia. Okay? That just has to do with how it reacts. I'll leave you to take a look at the book to see what's going on with that. You go through a radical mechanism as opposed to a metal catalyzed or a metal surface reaction, which puts you into the trans conformation as opposed to the cis. Okay? We will end there. I think the rest of them are our oxidation reactions. Oh, I went through and split that out. More summary. Yeah, the rest is oxidation. So I will post a lecture probably... I'll probably try and get that up either Thursday or Friday to cover the rest of the oxidation chapter.